everyone to this tutorial of ANSYS ACP. So today we're going to be studying the case of a bamboo fiber composite material, right, that's going to be tested under critical conditions. In this case, it's going to be submitted to a tensile test, all right? So we're going to check it out. This is a short tutorial that I'm recording for you so you can see how the process is done in ANSYS ACP module. And since I have the student edition of ANSYS, I cannot use the ACP post-processing data. So all of our information that we are going to do, that we are going to use for the processing, we are going to use it on the static structural module. All right, so we begin. First of all, thanking to the teacher Juan Guillermo Garcia, who was the one who instructed me on how to use the ACP and also the tutorials, right? So I'm recording this to save you some time in the future and not having any troubles with this. Let's begin by establishing the first parameter, which is the geometry. In this case, we have to go to the ANSYS design model module, and we have to check out what we are going to do and what do we want to test. In this case, we want to test this laminate, which is made out of bamboo fiber, which is already set it up on the engineering data sheet. This is pretty easy to set it up, so I'm just going straight up to the point. And yeah, we have to create surface body. In this case, we have the sketches normalized to the norms ATSM D390, right? So we create the surface body and we have this already. Once we have the geometry, we have to open up the ANSYS ACP module, all right? We will see something like this. We want to connect the setup of the ACP to the static structural model, just to transfer all the data from here to this model, all right? So what we are following here in the ACP is that we have to first check out that our material is defined in the tables, right? And here we can see on the Python module that it's already defined. Now we have to create a fabric. In this case, I'm using two fabrics, because I'm using two fibers in two opposite directions, but you can use only one and it will give the same results to you, all right? We can go on the 3D view, just click on the mouse scroll and go to a side view, right? We can see something like this. This is how the laminate looks like. It has a thickness of 1 unit, in this case, a millimeter. Now we can see that for creating the fabric, we go here to fabric properties and we set it up with the fiber that we want to be in there, the composite. In this case, bamboo fiber, right? I'm not going to change this. You have to change it, all right? And you're going to set up the thickness in millimeters, of course, of this fabric. In this case, mine is going to be 1 millimeter. You can just set it up for any value that you need for making your study. So that's our first fabric. The second fabric, it's the one that comes by default with the ACP module, with its epoxy carbon, 250 GPa of pre-break, right? We're not gonna use this, and I'm gonna tell you down here how we can avoid using this fabric, all right? Now we go to stack-ups. Stack-ups is basically the setup for the fibers that we are gonna use in the document, all right? And if we want to bring them on an angle, respecting to the origin axis. In this case, we can see the main rosette, that the origin axis is the z-axis, and how many degrees do we want it from that axis? 0 in my case. You can test it up to 45, you can test it up to 90. In my case, I did it for 0. So you select the fabric, right? This fabric that was over here, bamboo, select it and you put the angle, all right? Then we go to element sizes. In element sizes, you can literally just leave this like that because it will take out all the elements comprehended in the area of the test, of this laminate. And now we can go up to rosettes. So we have to set the rosettes correctly. Why? This is a really critical part and a critical step on the simulation of composite materials, especially in materials that have autotropic fibers, such as bamboo, width, etc., right? Because it can happen that the material can just go damping and move due to the momentum generated at the time that you apply the load. So it can go up like this or it can go down like this. To avoid this kind of physical phenomenon of occurring, we put these rosettes in opposite directions, right? As you can see here, entering on that detailed view, these rosettes allows us to have the z-axis looking upwards in one of those, and the rosette number one, who is looking downwards. So we can annulate those effects. This is not the only step that we have to do, right, before we can actually avoid this, but it is like the base step for avoiding this physical phenomenon, right? Now we move to oriented selection sets. In this case, we have to select the fabrics and the elements that we want. We have to put a rosette, all right, which is already here, the rosette one, a minimum angle of 0, and a direction for the axis, for the y-axis of 1, which means that it's looking upwards, as you can see over here. And we select all elements because it has to cover all the elements comprehended in the area of the laminate. We repeat the same thing, but in this case with -1, looking down, and that is how we can avoid the roughing of material, right? And the physical phenomenon when we apply the load, because ANSYS is blind in that term. So he's not going to differentiate if we are applicating, if we are applying the tensile load, and it's not going to, like, do it on a uniform way. It's just going to test it out, and assuming that the material is fixed from one of the points, but if the other is not fixed, it's just going to continue on and it can rotate and it can translate around itself. So this is why we have to avoid that, and we just want like a straight um, fiber movement, right? So this is what we are planning. Now we go to modeling groups. We have to create the plies, which is basically creating the fibers, all right? And we can see here in this option, if we click this, we can see the fiber directions, and we see that they are to 0 degrees in respect to the Z axis, and it's going to be the same for the ply number 2, all right? Which is based on the ply number 1. So you go here, you create it, right, like this. You just double click on this, you go create modeling group. It goes something like this, all right? You assign a name, and then you can model your ply in detail, and you can see that the oriented selection sets are the ones that we put with the ply material that we have set and the angle of the ply. All right, in the end, we can do a section cut to verify that everything is okay and it's in order. In this case, I'm not gonna like get into it because we already got it, right? I have already done it with the teacher Juan Guillermo. But this is like a way to prove that what we have done here, that all of these definitions were right. So we can look exactly how it goes, right? It has a thickness of 2 millimeters. If we update this, we will see it, all right? Because this thickness is only defined for one of those plies, but we have 2 plies, so 2 per 1, it's 2. So we're going to close the ACP, and we are right now transferring this data. You have to right click and transfer the shell data to the cell number 2 of the static structural model, and then we can see how we can set this up, setting the mesh and setting the border conditions, like the frontline conditions that we want to establish over here. All right, once we have reached the mechanical module, we see the entire thing already just put on place and ready to test it out. So we have the geometry input, we have the geometry parameter in general, we had it defined by the composite material that we have done, and the definition of the ANSYS ACP, and of course the engineering datasheet. And we also have the general coordinate system, which you can see over here, right? It says rosette in the corner, the bottom right corner, and now we can see the plies. So we want to establish, right, our conditions, our boundary conditions, to test this out. To do this a reality, we have to first of all establish a first support, and we're going to fix it in one of the edges of the laminate, just like I showed here. All right? Once one of the edges is fixed, we have to put a displacement. This displacement is exactly what we are looking for because this is the critical point of this test. We have to leave one of the axes completely free in order to get a result that is right with experimental data. This is mainly because a phenomenon occurs if I just leave this as free, is a phenomenon that I have told you before that basically can happen, that has a rotation or a displacement to the other axis. This means to this axis or this axis, and we don't want that. So we have to restrict those to 0 meters displacement on x and y axis, so it can only move in the z axis. All right, we can put the force, and for doing the right analysis, that was a mistake that I was committing back then as a student. I didn't know until my teacher told me. I was applying the force only in one of the edges. But the thing is, when you apply it and when you do it in one of the edges, that force is only being applied in that edge. It means that the force is not being distributed equally through the fibers. If you want to apply that all around the fibers and you want to really discover up the way that your fibers are going up through this test in the composite, and therefore getting the real results comparable to those done on lab, you basically have to put the force over entire face. So with the face selection tool, which is this, we can just press this and select and apply the force on this face. It will only apply on one of the plies, but only one is valid. The results will get the same as the laboratory. Now we go to solution. In the solution, we get the main information, and then we have the things that we want to see. The maximum principal stress, right? Maximum value in pascals. You can set up the units, so you can just get it in megapascals or gigapascals, as much as comfortable you see it for you. In this case, it's 219.99 megapascals, and that's the ultimate stress, like the maximum principal stress and the ultimate. If you compare it with the laboratory results, that's the ultimate. It's that value actually, and you can see also on a vectorized way by inserting on the solution, right, stress, and you can put the vector principle, and we can see this how the vectorial distribution of stresses is going around our laminate, and we can see that it's even, and that's how we prove that our result is correct. If you are still a little bit worried about the results, you can insert a probe of force reaction, and it has to be equivalent to the force that we are applying. And the reaction probe that we have to get, it's over here at the point where we fixed our geometry to the test. All right, we have all the constraints here: the equivalent elastic strain, the normal elastic strain, the normal stress, the stress intensity distribution, and with this, you can validate your laboratory experiments with the simulations in the ANSYS 2025 R2 student license. Thank you very much.